Hello there, and welcome back to Sleepy Tin Foil Hat. Tonight, we're going to drift far beyond the familiar world beneath your feet, far beyond the clouds, past the moon, and into the quiet red glow of a planet that has puzzled scientists, dreamers, and conspiracy hunters for generations. Mars has always felt different from the other worlds in our sky. Not just because of its color, not just because of its distance, but because of the strange feeling that it might be hiding a story we were never meant to fully understand. For thousands of years, people have stared up at that small reddish point of light and wondered why it looks the way it does. Ancient civilizations believed it was a sign of war, a wandering spirit, or a burning star that moved with a mind of its own. Later, astronomers began to notice something even stranger. Mars did not behave like the other planets. It moved backwards sometimes. It changed brightness in unusual ways. And when telescopes finally became powerful enough to reveal its surface, what we saw only created more questions than answers. At first, the red planet looked like a dry, silent desert. But the longer we looked, the more it seemed like a place that should not be so empty. Valleys stretched across its surface as if carved by rivers. Vast plains looked like ancient seabeds, and towering volcanoes rose higher than anything found on Earth. It felt less like a dead world, and more like a world that had lived a long time ago and then slowly went quiet. Tonight, we're going to explore one of the most mysterious questions about Mars. Not just what is on its surface, but where it came from in the first place. Because the deeper scientists have looked, the less certain they have become about how Mars was formed. Some theories say it should not even exist where it is. Others suggest it may have once been part of something much larger. And there are even ideas, whispered on the edges of science, that Mars might not have formed in the same way as the other planets at all. Before we go any further, if you enjoy these slow, late-night explorations into strange science and hidden theories, make sure to subscribe to Sleepy Tinfoil Hat and leave a comment telling me where in the world you're listening from tonight. I always like seeing how far these quiet little journeys travel. Somewhere out there, someone else is listening in the dark too, wondering about the same mysteries, and that makes the universe feel a little smaller. Now, get comfortable. Let your shoulders drop. Let your breathing slow down. There's nothing you need to do right now except listen and let your mind wander across space with me. When scientists first tried to understand how the planets formed, the idea seemed simple. Long ago, before the sun was fully born, there was a huge cloud of gas and dust floating in space. Over time, gravity pulled that cloud together, and most of the material gathered in the center to form the sun. The rest of the dust slowly clumped together, piece by piece, until it formed the planets we know today. According to this model, the inner planets, Mercury, Venus, Earth, and Mars, should all have formed in roughly the same way. They should be made from similar materials, built from the same cloud, shaped by the same forces. And in many ways, that idea works. Earth and Venus are very similar in size. Mercury fits the pattern of a smaller rocky world close to the Sun. But Mars does not quite fit. Mars is smaller than scientists expected it to be. Much smaller. In fact, when researchers run computer simulations of how planets should form, Mars usually comes out far larger than it really is. Something seems to have stopped it from growing. Something prevented it from becoming a world as big as Earth. And that small difference changes everything. Because in the early solar system, size mattered. A larger planet could hold on to heat longer. It could keep an atmosphere. It could keep oceans. A smaller one would cool faster, lose its air, and slowly turn into the cold, dry world we see today. Mars looks exactly like a planet that stopped growing too soon. That alone would be strange enough. But the mysteries don't end there. When scientists studied Martian meteorites, pieces of Mars that landed on Earth after ancient impacts, they discovered something unexpected. The chemical makeup of Mars is slightly different from Earth's. Not wildly different, but different enough to suggest that the material that formed Mars may not have come from the exact same region of space as the material that formed our planet. That raises a strange possibility. What if Mars formed somewhere else and ended up where it is now? It sounds like science fiction, but in the early days of the solar system, planets did not sit quietly in their orbits the way they do today. Everything was moving. Everything was colliding. Giant worlds were shifting positions, pulling smaller bodies with them, throwing debris across millions of kilometers of space. Some scientists believe that Jupiter, the largest planet in the solar system, may have played a huge role in shaping the fate of Mars. In certain models, Jupiter did not stay where it is now. It may have moved inward toward the Sun before drifting back out again, and as it moved, its gravity would have disturbed the material that was supposed to form Mars. Imagine trying to build a sandcastle while someone keeps dragging their hand through the sand. The pieces never get the chance to come together properly. In this idea, Mars is not small because it was meant to be small. Mars is small because something interrupted its creation. And if that is true, then Mars is not just another planet. It is a leftover piece of a solar system that almost formed differently. The more scientists studied the red planet, the more it started to look like a frozen record of the early solar system. Earth has changed too much. Volcanoes, oceans, and plate tectonics have erased most of the evidence of its earliest days. But Mars never grew large enough for that kind of activity to continue. Its surface is ancient. Its scars are still visible. Its history is still written in stone. And that makes it one of the most valuable clues we have about how everything began. But some researchers have gone even further. They've suggested that Mars might not just be a small planet, but a fragment, a piece of something that broke apart long ago. There are theories about lost planets, destroyed worlds, and early collisions so violent that entire bodies could have been shattered and scattered across the solar system. Most of these ideas stay on the edges of science, not because they are impossible, but because the evidence is hard to prove. Space is a place where clues disappear easily. After billions of years, only small hints remain. Still, the fact that Mars does not fit perfectly into the standard story keeps those theories alive. And the more we explore Mars, the more those questions seem to grow instead of fade. Orbiters have mapped every valley, every crater, every frozen plain. Rovers have rolled across ancient lake beds. Satellites have scanned beneath the surface looking for hidden ice, hidden water, hidden structures buried under dust for millions of years. Each discovery answers one question and quietly creates another. Because Mars looks less like a world that never lived, and more like a world that lost something it once had, something that disappeared. And when a planet loses something that big, the question becomes impossible to ignore. What really happened there? And how far back does that story go? We're going to keep drifting deeper into that mystery next, into the earliest days of the solar system, when planets were still forming, and when Mars may have taken a path very different from the one we were taught. In the earliest moments of the solar system, nothing looked the way it does now. There were no clear orbits, no calm rotations, no quiet nights with planets moving slowly across the sky. Instead, everything was crowded, chaotic, and constantly changing. The young sun was surrounded by a thick disk of dust and gas, spinning slowly like a vast cosmic storm. Inside that disk, tiny grains of rock and metal were colliding, sticking together, breaking apart, and then sticking together again. Over time, those grains became pebbles. The pebbles became boulders. The boulders became objects large enough for gravity to take hold. And once gravity started pulling things together, the process began to speed up. Larger pieces attracted more material, growing faster than the smaller ones around them. In the region where Earth formed, this process worked almost perfectly. Enough material gathered, enough time passed, and a full-size planet slowly took shape. But in the region where Mars sits today, something interrupted the process. When scientists run simulations of the early solar system, they expect the area between Earth and Jupiter to have had plenty of material to form another planet as large as Earth, maybe even larger. Instead, what we see today is a small planet, Mars, and beyond it, the asteroid belt, a scattered collection of broken pieces that never became a world at all. It almost looks as if something swept through that region and prevented it from ever finishing. One of the leading ideas is known as the Grand Tack theory, and even though the name sounds gentle, the event it describes would have been anything but. According to this theory, Jupiter did not always sit where it does now. In the beginning, it may have formed farther from the Sun, then slowly moved inward, pulled by the gravity of the thick gas disk surrounding the young star. As Jupiter drifted inward, its enormous gravity would have disturbed everything in its path. Dust clouds would have been scattered, growing planets would have been disrupted, and smaller worlds might have been thrown off course entirely. In this model, Jupiter moved inward until it reached about the distance where Mars now orbits. And then something unexpected happened. Saturn formed, and its gravity began pulling on Jupiter, changing its path. Instead of continuing toward the Sun, Jupiter reversed direction and moved outward again, like a ship turning around in the middle of a storm. That turn, the tack, as astronomers call it, may have reshaped the entire inner solar system. If Jupiter really passed through that region, even for a short time, it could have scattered much of the material that was supposed to form Mars. Instead of growing into a full-size planet, Mars may have been left with only a small amount of the original building material. Not because it failed, but because the pieces it needed were taken away, and that would explain something scientists had struggled with for decades. Mars looks like a planet that started forming at the same time as Earth, but stopped much earlier. Its interior cooled quickly. Its volcanic activity slowed down sooner. Its magnetic field faded long before Earth's did. All signs of a world that never reached its full size. But the Grand Tack theory raises another strange possibility. If Jupiter moved that much, then the early solar system was not a neat, orderly place at all. Planets may have changed positions. Orbits may have shifted. And some worlds might not have ended up where they originally formed. That leads to an idea that sounds almost impossible at first. What if Mars didn't form exactly where it is now? When scientists study the chemical fingerprints of planets, they can sometimes tell where the original material came from. Different regions of the early solar system had slightly different mixtures of elements, depending on temperature, distance from the Sun, and how the dust cloud evolved over time. Earth and Venus look very similar in composition, which makes sense if they formed close to each other. But Mars shows subtle differences that suggest it may have formed from material that came from farther away. Not from the outer solar system, but not exactly from the same place as Earth either. It's as if Mars belongs to the inner planets, but not perfectly. Some researchers think that when Jupiter moved, it may have pushed material from different regions together, mixing the ingredients of the solar system in ways that left Mars with a slightly different recipe. Others think something even stranger may have happened. There is a possibility, still debated, still uncertain, that Mars might be the surviving core of a planet that never fully formed, or even a fragment of a larger body that broke apart early in the solar system's history. In the beginning, there were likely dozens of protoplanets, worlds that were forming at the same time, competing for material. Collisions between those early worlds would not have been gentle. They would have been violent beyond imagination. When planets collide, they don't just crack. They melt. They shatter. Pieces can be thrown into space at incredible speeds. some falling back together, others drifting away forever. We know this happened at least once in our own history. The leading theory for the Moon's origin says that a Mars-sized world struck Earth billions of years ago, sending debris into orbit that later formed the Moon. If something like that happened elsewhere, if another young planet was destroyed before it finished forming, some of the pieces might still be here today. Mars could be one of them. Not a complete planet in the way Earth is, not a simple leftover either, but something in between. A survivor of a time when the solar system was still deciding what it would become. And the surface of Mars seems to carry the marks of that ancient violence. Its crust is thick and uneven. One hemisphere looks completely different from the other. The northern half of the planet is low and smooth, while the southern half is high and covered in craters. This difference is so extreme that some scientists believe Mars may have been hit by something enormous early in its history, an impact so large that it reshaped half the planet. If that is true, then Mars is not just a small planet. It is a wounded one, a world that was changed before it ever had the chance to grow into what it might have been. And yet, even after all of that, Mars still managed to keep signs of something unexpected. Because when we look at the valleys, the dry riverbeds, the minerals that form in water, and the strange patterns in its rocks, it becomes hard to believe that Mars was always the cold desert we see today. It looks like a place that once had flowing water, a thicker atmosphere, maybe even a warmer climate, which raises a question that feels even more mysterious than how Mars formed. If Mars started small, if it lost material early, if it cooled faster than Earth, how did it ever manage to look so much like a world that could have been alive? To understand that, we have to go deeper into the planet itself, into its core, its magnetic field, and the strange moment when Mars seems to have changed forever. To understand why Mars looks like a world that once lived and then slowly went silent, scientists had to look beneath the surface. Not just at the rocks and valleys we can see, but at the structure hidden deep inside the planet. Because the inside of a world tells a story that the surface alone cannot explain. Every rocky planet begins its life hot. When planets form, the constant collisions, the pressure of gravity, and the decay of radioactive elements all generate enormous heat. In the early solar system, Earth, Venus, and Mars were not cold places at all. They were molten worlds, covered in oceans of magma, with surfaces that would have glowed faintly red under a dark sky. As a planet cools, its interior begins to separate into layers. Heavy metals sink toward the center. Lighter rock rises toward the surface. Over time, this creates a core, a mantle, and a crust. On Earth, that process is still happening even now. The core remains hot, the mantle slowly moves, and the crust shifts in huge plates that slide past each other. Mars should have gone through the same process, and in the beginning, it probably did. But there is a difference between a planet that grows large and a planet that stays small. A larger planet can hold on to its heat for billions of years. A smaller planet loses heat much faster. Mars, being only about half the size of Earth, cooled quickly compared to its neighbors. And when a planet cools too fast, something important can disappear. Something that most people never think about when they imagine a world. Its magnetic field. Earth has a strong magnetic field, created by the motion of molten metal in its core. That invisible field stretches far into space, forming a protective bubble around the planet. It shields the atmosphere from the constant stream of charged particles coming from the sun, known as the solar wind. Without that protection, a planet's atmosphere can slowly be stripped away. Mars once had a magnetic field too. We know this because its ancient rocks still carry traces of magnetism, frozen into them from a time when the planet's core was active. But at some point, long ago, the magnetic field of Mars faded and disappeared. And when it did, everything began to change. Without a magnetic shield, the solar wind had a direct path to the Martian atmosphere. Over millions of years, the constant flow of particles began to erode the air, molecule by molecule, pushing it out into space. The thicker the atmosphere became, the faster it was lost. It was not a sudden event. It was slow, almost silent. But over time, the sky above Mars grew thinner. The pressure dropped. The temperature fell. Water that once flowed on the surface could no longer stay liquid. It either froze into the ground or escaped into space. Lakes dried. Rivers stopped. Whatever warmth Mars once had began to fade, leaving behind the cold desert we see today. And yet, the evidence that it was once different is everywhere. From orbit, Mars is covered in channels that look like dried riverbeds. Some stretch for hundreds of kilometers, winding across the landscape in ways that are hard to explain without flowing water. There are minerals that only form in the presence of liquid water. There are layers of sediment that look like they were deposited at the bottom of ancient lakes. Even the shape of the northern hemisphere suggests that something huge once filled it. The low, smooth plains in the north look like the floor of a vast basin, leading some scientists to wonder if Mars may have once had an ocean that covered nearly a third of the planet. An ocean on Mars sounds impossible now. The air is too thin. The temperature is too low. The water would freeze or boil away almost instantly. But the rocks tell a different story. They say that long ago, Mars had enough heat, enough atmosphere, and enough stability to hold liquid water for millions of years, maybe longer. And if that was true, then Mars was not just a broken planet. It was once a world that could have been alive. That idea changed everything about how scientists looked at the red planet. Mars stopped being just another object in the sky. It became a place with a history, a timeline, a past that might have been very different from its present. And that past has another strange detail that makes the origin of Mars even more mysterious. When researchers studied the ages of Martian rocks, they noticed something unusual. Mars seems to have formed very quickly compared to Earth. While Earth continued growing for tens of millions of years, Mars appears to have reached most of its size much earlier, almost as if it formed fast, and then stopped. That fits with the idea that something interrupted the process. Maybe Jupiter's movement scattered the remaining material. Maybe a giant impact changed the planet's future. Maybe Mars was always meant to be smaller, but formed in a region where conditions were different from what we expected. There is also the strange difference between the two halves of the planet. The southern hemisphere of Mars is old and heavily cratered, covered in the marks of ancient impacts. The northern hemisphere is smoother, lower, and looks younger, as if something erased the older surface. This difference is so extreme that scientists gave it a name: the Martian dichotomy. One half of the planet looks ancient, the other half looks like it was reshaped. One explanation is that Mars was struck by an object so large that it changed the entire structure of the planet. Not a normal asteroid, but something the size of a small world. The impact would have melted huge parts of the crust, creating a giant basin that later became the northern lowlands. If that happened, then Mars carries a scar from one of the biggest collisions in the history of the solar system. And events like that could also affect the inside of the planet. A massive impact could disturb the core, change the way heat flows through the mantle, and even weaken the magnetic field. It might not destroy a planet, but it could change its future forever. When you start putting all these pieces together, Mars begins to look less like a simple planet and more like a survivor. A world that formed early was shaken by the movement of giant planets, possibly struck by something enormous, cooled faster than expected, lost its magnetic shield, lost its atmosphere, and slowly turned into the quiet red desert we see now. But even with all that, there is still one mystery that refuses to go away. because Mars should have been completely dead long ago. And yet, when we send spacecraft there, when we scan beneath the surface, when we study the chemistry of its soil, we keep finding hints that something is still there. Not cities, not machines, not anything dramatic. Just small, quiet signs that the story of Mars might not be finished yet. And to understand why, we have to look at something even stranger than its origin. We have to look at the possibility that Mars may have changed more than once. When scientists first began sending spacecraft to Mars, they expected to find a simple world, a cold planet covered in dust with a history that ended billions of years ago. The idea was straightforward. Mars formed, cooled, lost its atmosphere, and became frozen in time. A quiet place where nothing new had happened for ages. But the closer we looked, the harder it became to believe that the story was that simple. The first orbiters sent back images of a surface far more complicated than anyone expected. Instead of a flat desert, Mars showed signs of ancient floods, collapsed ground, layered cliffs, and strange patterns that looked almost like something had changed the planet long after it was supposed to be dead. At first, scientists assumed these features must all be very old, leftovers from a time when Mars was young and active. But some of the shapes looked too sharp, too fresh, too well preserved. On Earth, wind, water, and tectonic movement erase old features quickly. On Mars, things last longer, but even so, some of these formations looked like they might not be as ancient as we thought. That created a strange possibility. Maybe Mars did not just change once. Maybe it changed more than once. One of the biggest clues came from studying the volcanoes of Mars. The red planet has the largest volcano in the entire solar system, a massive mountain called Olympus Mons. It rises nearly 3 times higher than Mount Everest and stretches hundreds of kilometers across. It is so large that if you stood on its slope, you would not even realize you were on a mountain at all. Olympus Mons should not exist on a small planet. On Earth, volcanoes rarely grow that large because the surface is always moving. The crust is broken into plates that shift slowly over time. When a volcano forms, the plate moves, and the hotspot underneath creates a new volcano somewhere else. This spreads the activity out. Mars does not have plate tectonics like Earth. Its crust is more like one solid shell. That means when a volcano starts forming, it stays in the same place, and the lava keeps building on top of itself for millions of years. That is how Olympus Mons became so enormous. But the strange part is not just its size. Some of the lava flows on Mars look younger than expected. Not young in human terms, but younger than scientists thought a planet like Mars should still be able to produce. There are regions where the surface looks like it was reshaped long after the planet was supposed to have cooled completely. That suggests Mars stayed active longer than it should have. And that leads to another mystery about its origin. If Mars formed small and cooled fast, its interior should have gone cold early in its history. The core should have solidified. The mantle should have stopped moving. Volcanoes should have shut down billions of years ago. But the surface does not fully match that idea. It looks like Mars held on to some of its internal heat longer than expected, almost as if something inside the planet did not cool the way we thought it would. To understand that, scientists started looking at the core of Mars more closely. Recent missions, including landers that can detect tiny vibrations in the ground, have given us new clues about what the inside of Mars looks like. By studying Marsquakes, small tremors that travel through the planet, researchers can estimate the size and state of its core. What they found was surprising. Mars appears to have a larger liquid core than expected for a planet its size. Instead of being mostly solid, the center of Mars may still contain a significant amount of molten metal. That means the planet did not cool as quickly as simple models predicted. Something slowed the cooling. Maybe the material Mars formed from was different. Maybe early impacts changed the way heat moved through the planet. Maybe the core contains elements that keep it molten longer. Or maybe the way Mars formed was never as straightforward as we thought. There is another clue that makes the origin of Mars even more unusual. The crust of Mars is much thicker than Earth's. In some places, it may be more than twice as thick. A thick crust can trap heat inside the planet, acting like insulation, preventing the interior from cooling too fast. But a crust that thick is hard to explain if Mars formed exactly the same way as Earth. It suggests that the early history of Mars was different. Not completely different, but not identical either. Some scientists think Mars may have formed in a region where there was less material, less energy, and fewer collisions, allowing it to develop a thicker outer layer before the interior fully settled. Others think a giant impact early in its life could have reshaped the planet so dramatically that its internal structure never followed the usual pattern. And then there are the ideas that sit just outside mainstream science, the ones that researchers don't always talk about openly, but that never completely disappear. Ideas that Mars might be a remnant of something older. Not older than the Sun, not older than the solar system, but older than the current arrangement of planets. A world that formed during a time when everything was still unstable, when bodies were forming and breaking apart, when orbits were shifting, and when the solar system looked nothing like it does now. In those early millions of years, it is possible that more planets existed than the ones we see today. Some may have collided and merged. Some may have been thrown out of the solar system entirely. Some may have broken apart, leaving fragments that later became the worlds we know. Mars, in this view, would not be an incomplete planet. It would be a survivor. A piece that remained after the chaos settled, still carrying the marks of a past that the larger planets have erased. And the more we study Mars, the more it feels like a record that was never rewritten. Earth has oceans that recycle its crust. Venus has heat that reshapes its surface. Even the moon was changed by impacts for billions of years. Mars, on the other hand, seems frozen between past and present. Its valleys still show where water once flowed. Its volcanoes still show where fire once rose. Its rocks still hold magnetism from a field that vanished long ago. It is like a snapshot of the early solar system, preserved almost by accident. But there is one more mystery that makes the origin of Mars feel even stranger. Because when scientists compare Mars to Earth, they see something unexpected. The two planets are different in size, different in structure, different in atmosphere, and yet they look like they were once much more alike than they are now. Almost as if, at one point in the distant past, Mars was closer to being an Earth-like world than we ever imagined. And if that is true, then the biggest question is not just how Mars formed. It is how it changed from something that might have been alive into the silent red planet we see today. The idea that Mars might once have been more like Earth is not just speculation. Over the last few decades, every mission sent to the red planet has added another small piece to a picture that feels both familiar and unsettling. Because the more we learn, the more Mars looks like a world that followed the same path as Earth in the beginning, and then slowly drifted away from it. When the solar system was young, the sun was not as bright as it is today. That means the inner planets should have been colder than they are now. Earth somehow stayed warm enough for liquid water, likely because of a thick atmosphere filled with greenhouse gases that trapped heat. Mars, being farther from the sun, should have been even colder. And yet, the surface of Mars shows clear signs that water once flowed freely. There are valleys that branch like river systems. There are deltas where water appears to have emptied into standing lakes. There are minerals that form only when rock sits in liquid water for long periods of time. These are not small traces. They suggest that Mars may have once had rivers, lakes, and possibly even shallow seas. For that to happen, the planet must have had a much thicker atmosphere than it has now. the air would need enough pressure to keep water from instantly boiling away. It would need enough greenhouse gases to keep temperatures above freezing. In other words, Mars must once have had conditions that were at least somewhat similar to early Earth. That idea changes the way we think about its origin. If Mars formed too small and cooled too quickly, how did it manage to keep an atmosphere long enough for water to exist? Why did it not lose everything immediately? Why does it show signs of a warm, wet past before turning into the cold desert we see today? One possible answer lies in the timing of its formation. Some studies suggest that Mars formed very early, earlier than Earth finished forming. In the first few million years of the solar system, there was still a lot of radioactive material trapped inside growing planets. These elements produce heat as they decay, and in the early days, that heat would have been much stronger than it is now. If Mars formed quickly, it may have trapped more of that early heat inside its core. That extra warmth could have kept the interior active long enough to power volcanoes, create a magnetic field, and release gases into the atmosphere through eruptions. Volcanoes play a huge role in shaping a planet's air. On Earth, much of our atmosphere came from gases released by volcanoes billions of years ago. Carbon dioxide, water vapor, and other gases were pushed out of the interior and slowly built up the air we breathe today. Mars likely went through the same process. For a time, the planet may have had enough volcanic activity to create a thick atmosphere and allow water to exist on the surface. But because Mars was smaller, that activity did not last forever. As the interior cooled, the volcanoes slowed down. As the core cooled, the magnetic field weakened. As the magnetic field faded, the atmosphere began to escape. And once the atmosphere started to disappear, the rest followed. Without enough air, the pressure dropped. Without pressure, water could not stay liquid. Without water, the climate changed. Mars slowly became the world we see now. But even this explanation leaves strange details behind. For example, some of the biggest volcanoes on Mars appear to have stayed active long after the planet should have cooled. Olympus Mons and the surrounding volcanic region show signs that eruptions may have continued for hundreds of millions of years, maybe even longer. That suggests Mars did not cool evenly. Something inside the planet kept certain regions warm longer than expected, as if the heat was trapped or concentrated instead of fading away smoothly. This uneven cooling could be connected to the thick crust, the large core, or the early impacts that reshaped the planet's interior. There is also the mystery of the lost atmosphere itself. Scientists know that Mars lost most of its air, but the exact process is still being studied. Some of it escaped into space because of the solar wind. Some may have been locked into the ground as ice or minerals. Some may have been blown away by massive impacts early in the planet's history. In the early solar system, collisions were common. Objects the size of mountains, continents, or even small planets could strike each other at incredible speeds. An impact large enough could remove huge parts of a planet's atmosphere in a single event. There is evidence that Mars was hit many times, including at least one collision so large that it may have created the giant basin that forms the northern lowlands. If that impact happened after Mars had already built a thick atmosphere, it could have stripped away a large part of it all at once. That would mean Mars did not slowly lose its air. It may have lost it in stages, a little at a time, then suddenly, then slowly again. And that kind of history makes the origin of Mars feel less like a simple story and more like a series of accidents. A world that formed early, grew fast, was disturbed by the movement of giant planets, struck by enormous impacts, cooled unevenly, lost its magnetic field, and watched its atmosphere disappear piece by piece. When you look at Mars today, you are not just seeing a planet. You are seeing the result of everything that went wrong, or everything that happened differently. And yet, even with all that loss, Mars still keeps traces of what it once was. Frozen water sits beneath its surface. Ice fills its polar caps. Ancient lake beds wait in dry basins. Minerals formed in water still lie in the dust. It is like walking through the ruins of a place that used to be alive. And that feeling has led some scientists to wonder about something even more unsettling. Not just whether Mars once had water, but whether Mars once had time. Time when conditions were right. Time when the atmosphere was thick. Time when the planet was warm enough. Time long enough for something to begin. To understand that possibility, we have to go even deeper into the earliest era of Mars, back to a time when the planet was still young, still active, and still very different from the silent world we know now. When we talk about the early days of Mars, we are talking about a time so far in the past that even the oldest rocks on Earth can barely remember it. More than 4 billion years ago, the solar system was still settling down. Planets were forming, colliding, reshaping themselves, and slowly finding the orbits they would keep for the rest of their lives. During that time, Mars may have been at its most alive. Not alive in the sense of plants or animals, at least not as far as we know, but alive in the sense that everything on the planet was still moving, still changing, still full of energy. The core was hot, volcanoes were active, the atmosphere was thicker. Water may have flowed across the surface in ways that would be impossible today. This period is sometimes called the Noachian era, named after one of the oldest regions on Mars. It represents the earliest chapter of the planet's history, when most of the large valleys and impact basins we see today were formed. It was a time when Mars looked less like the cold desert we imagine, and more like a world that could have had weather, clouds, rain, and rivers. The evidence for this era is written all over the surface. Huge channels cut through the highlands as if carved by flowing water. Some of them are so large that they stretch for thousands of kilometers. There are places where the land looks like it collapsed after water drained away underground. There are minerals like clay and sulfate that only form when rock sits in water for a long time. These are not the signs of a planet that was always frozen. They are the signs of a planet that once had a climate. But that brings us back to the same question again. If Mars was small and cooled quickly, how did it manage to keep a warm enough environment for so long? Why does it look like a world that had a real chance to become something more? One possibility is that Mars formed during a moment in the solar system when conditions were very different from what they are now. In the beginning, the young sun was more active. It gave off stronger solar winds, but it may also have produced more energy in certain wavelengths that could affect a planet's atmosphere in unexpected ways. At the same time, the early solar system was full of debris. Asteroids, comets, and leftover pieces of planet formation were still moving in unstable orbits. Many of these objects struck the planets, delivering not only energy, but also water and gases. Some scientists believe that much of the water on Earth may have come from impacts with icy bodies from the outer solar system. If that happened on Earth, it may have happened on Mars too. In fact, Mars may have received a large amount of water early in its history, enough to create lakes, rivers, and possibly even oceans for a time. But Mars could not hold on to those conditions forever, because the same early chaos that may have given Mars water could also have taken things away. Large impacts could strip away atmosphere. Solar radiation could erode the air once the magnetic field weakened. Volcanic activity could slow as the interior cooled. Little by little, the planet would begin to lose the things that made it warm. And yet, the timeline of that change is still not completely clear. Some studies suggest Mars lost its magnetic field very early, maybe within the first few 100 million years. Others suggest it lasted longer. Some evidence hints that water may have existed on the surface even after the magnetic field began to weaken, which means the atmosphere might have survived longer than expected. That uncertainty keeps the mystery open. Because if Mars stayed warm longer than we think, then the window for something unusual to happen becomes wider. When scientists talk about habitability, they don't mean a planet has to look exactly like Earth. They only mean the conditions need to allow liquid water, stable temperatures, and enough time for chemical reactions to become more complex. On Earth, life appeared surprisingly early once the conditions were right. The oldest evidence suggests that simple life may have existed less than 1 billion years after the planet formed. That is a short time on a cosmic scale. If Mars had water, heat, and atmosphere during its early history, then it may also have had that same opportunity. That idea makes the origin of Mars feel even more important. Because if Mars formed differently, if it cooled differently, if it lost its atmosphere differently, then its entire history may have followed a different path from Earth, even though the two planets started out so similar. There is another detail that makes Mars feel like a world that almost became something more. Unlike Earth, Mars never developed strong plate tectonics. On our planet, the surface is always being recycled. Old crust sinks, new crust forms, and the record of the distant past is slowly erased. Mars does not do that. Its surface stayed mostly in place for billions of years. That means the oldest parts of Mars are still there. The rocks that formed when the planet was young are still exposed. The valleys carved by ancient water are still visible. The scars from early impacts have not been completely erased. Mars is like a museum of the early solar system. And sometimes, when scientists look closely at those ancient regions, they find things that are hard to explain with simple models. Patterns that look like flowing water long after the atmosphere should have been thin. Minerals that suggest long periods of stability. Features that hint the planet stayed active longer than expected. Each of these clues is small on its own, but together, they make the story of Mars feel less certain. Maybe the planet did not cool as quickly as we thought. Maybe the atmosphere lasted longer. Maybe the early solar system was more unpredictable than our models show. Or maybe Mars followed a path that almost led somewhere else, before something changed it forever. Because when we reach the end of the Noachian era, something seems to shift. The rivers stop appearing. The atmosphere grows thinner. The surface becomes colder and drier. It is as if the planet crosses a line, moving from a world that could support water to a world where water can only exist as ice. And whatever caused that change may be one of the biggest secrets in the entire history of Mars. In the next part, we're going to look at that turning point, the moment when Mars seems to have lost its chance to stay alive, and the strange theories about what might have pushed the planet past the point where it could never go back. At some point in the distant past, Mars crossed a line that it never returned from. Before that moment, the planet showed signs of warmth, flowing water, and an atmosphere thick enough to support weather. After that moment, the surface began to dry, the air began to thin, and the planet slowly turned into the cold, silent world we see today. Scientists are still trying to understand exactly when this change happened, but most evidence points to a long transition rather than a single event. Mars did not suddenly freeze overnight. Instead, it seems to have lost its habitability step by step, as if one piece of the system failed, then another, and then another, until the balance that once kept the planet alive could no longer hold. The first piece to go may have been the magnetic field. A magnetic field is easy to ignore because we cannot see it, but for a planet, it can be the difference between survival and slow destruction. Earth's magnetic field protects our atmosphere from the constant stream of charged particles coming from the sun. Without that shield, those particles would gradually strip away the air, pushing it into space over millions of years. Mars once had a magnetic field, and the evidence for it is locked inside ancient rocks scattered across the southern highlands. These rocks still carry tiny magnetic signatures, showing that they formed when the planet's core was active and generating a global field. But those signatures disappear in younger regions, meaning the magnetic field faded very early in the planet's history. Why it faded is still one of the biggest questions. The simplest explanation is that Mars cooled too fast. Because the planet is smaller than Earth, its interior lost heat more quickly. Once the core cooled enough, the motion of molten metals slowed down, and without that motion, the magnetic field could no longer exist. But the timing is strange. Some evidence suggests the magnetic field may have disappeared while Mars still had water on its surface. That would mean the atmosphere did not vanish immediately. Instead, the planet may have spent millions of years with a weakening shield, slowly losing its protection while the climate struggled to stay stable. During that time, the solar wind would have begun to chip away at the upper atmosphere, one particle at a time. Each impact carried a tiny bit of gas into space. Over thousands of years, the loss would have been almost invisible. Over millions of years, it would have changed everything. The air became thinner. The pressure dropped. The planet cooled. As the atmosphere weakened, water on the surface became harder to keep in liquid form. Instead of flowing in rivers, it began to freeze into the ground or escape into space as vapor. Lakes dried up. Valleys stopped forming. The cycle that once kept the planet warm began to break apart. And yet, even as Mars was losing its atmosphere, something else may have been happening at the same time. Some scientists believe that Mars experienced a series of enormous impacts during this period, collisions large enough to change the structure of the planet itself. The biggest of these may have created the giant basin that covers much of the northern hemisphere, a depression so large that it looks like half the planet was pushed inward. If that impact happened while Mars still had an atmosphere, the effect could have been devastating. An object the size of a small moon striking the planet at high speed could throw huge amounts of gas into space. Shock waves would travel through the crust, melting rock, reshaping the surface, and possibly disturbing the core. Even if the planet survived, the balance that kept it warm might never have recovered. Some researchers think that event may have been one of the turning points in Mars's history. Not the only one, but one of the moments when the planet moved further away from the path that might have made it more like Earth. After that time, the surface of Mars begins to look different. The oldest regions are full of river valleys and signs of long-term water. Later regions show fewer and fewer of those features. Instead, we see dry channels, floodplains that look like they formed quickly and then vanished, and large areas where wind seems to have become the dominant force shaping the land. It is as if the planet was running out of time. The volcanoes kept erupting for a while, releasing gases that may have helped the atmosphere survive a little longer. But without a magnetic field, the air could not stay forever. Each eruption added something, and each solar storm took something away. Slowly, the balance tipped. By the time Mars entered the era scientists call the Hesperian period, the planet was already colder and drier than before. Water still appeared occasionally, but it no longer flowed the same way. Instead of long rivers, there were sudden floods, possibly caused by underground ice melting or pressure building beneath the surface. These floods could carve enormous channels in a short time, leaving behind features that look dramatic but brief, like the last bursts of activity from a world that was shutting down. Eventually, even those signs faded. Mars entered the Amazonian era, the period that continues today. During this time, the planet became mostly dry, mostly frozen, and mostly quiet. Dust storms replaced rain. Ice replaced lakes. The atmosphere thinned to less than 1% of Earth's pressure. From that point on, Mars looked almost the way it does now. A cold desert, a silent sky, a planet that feels empty. But the strange thing is that the story never feels completely finished. Because even in the Amazonian era, there are hints that Mars did not become completely inactive. Some regions look younger than expected. Some slopes show dark streaks that appear and disappear, as if something still moves beneath the surface. There are signs of underground ice, buried water, and maybe even pockets of warmth deep below the crust. Nothing dramatic, nothing obvious, just small clues that the planet may not be as dead as it seems. And when you look back at the origin of Mars, all the way to the beginning, those clues make the story feel even stranger. A planet that formed differently. A planet that stopped growing too soon. A planet that may have lost its atmosphere in pieces. A planet that almost looked like Earth once, and then slowly became something else. It makes you wonder if Mars was always meant to end this way, or if it was one small change away from becoming a completely different world. In the next part, we're going to explore some of the more unusual ideas scientists have considered about the origin of Mars. Ideas about lost planets, early collisions, and the possibility that the solar system once looked very different from the one we know today. When scientists try to understand the origin of Mars, they usually begin with the standard model of how the solar system formed. A cloud of gas and dust collapsed. The sun formed in the center, and the planets slowly built themselves out of the material left behind. Most of the time, that model works very well. It explains why the planets orbit in the same direction, why the inner worlds are rocky, and why the outer ones are made mostly of gas. But Mars has always been one of the planets that does not fit perfectly into that picture. It is smaller than expected. Its chemistry is slightly different. Its surface looks like a frozen record of a past that ended too early. And because of that, scientists have spent decades exploring ideas that go beyond the simplest explanation. Not wild guesses, not science fiction, but serious possibilities that come from the fact that the early solar system was far more chaotic than we once believed. In the beginning, there may not have been just 4 rocky planets forming near the sun. There may have been many more. When computer models simulate the first few million years of planet formation, they often produce dozens of growing worlds instead of just a handful. These early worlds, sometimes called planetary embryos, would have been similar in size to the Moon, Mars, or even Earth. They moved through the disk of dust and gas, pulling material toward themselves, colliding with each other, and sometimes merging into larger bodies. In this kind of environment, nothing stayed stable for long. A growing planet could be knocked into a new orbit. 2 planets could collide and become one. A third could be thrown outward into deep space. The solar system we see today may simply be the final survivors of a much larger group. This idea becomes especially interesting when we look at the region between Mars and Jupiter. Today, that area contains the asteroid belt, a scattered collection of rocky fragments that never formed a full planet. For a long time, scientists thought the asteroid belt was just leftover material that never came together. But newer models suggest something more complicated. It may not just be leftover material. It may be what remains after something prevented a planet from forming there, or what remains after a planet was broken apart. The gravity of Jupiter plays a huge role in this region. Because Jupiter is so massive, its pull can disturb the orbits of nearby objects, making it harder for them to come together. That alone could explain why the asteroid belt never became a planet. But some simulations show that even with Jupiter's influence, the inner solar system should still have formed a planet larger than Mars. Instead, we see a small Mars and a belt of debris. That mismatch has led to the idea that the early solar system may have gone through a period of instability when the giant planets moved from their original positions. According to some versions of this theory, Jupiter and Saturn may have shifted their orbits dramatically during the first 100 million years, changing the entire layout of the solar system. If that happened, the effects would have been enormous. Material that was supposed to build one planet could be scattered. Growing worlds could be pushed inward or outward. Entire regions could be emptied of the dust needed to form a large planet. Mars might be the result of that disturbance. Instead of forming in a calm, steady environment, it may have grown in a region that was constantly being reshaped by the motion of the giant planets. That would explain why it never reached the size of Earth, and why the asteroid belt ended up as a collection of fragments instead of a single world. But there is another idea, one that sounds even stranger, yet comes from the same kind of scientific modeling. Some researchers have suggested that there may once have been an additional planet in the early solar system, a world that no longer exists today. Not a huge planet like Jupiter, but something roughly the size of Mars or Earth. In these models, the extra planet eventually became unstable and was either thrown out of the solar system or collided with another world. If something like that happened, the consequences would still be visible today. Orbits would shift, material would be scattered. Planets that were forming would end up smaller or larger than expected. Mars could be one of the worlds that survived that period of instability, but not without being changed by it. There is also the possibility that Mars itself was involved in one of those early collisions. We know that Earth experienced a massive impact that created the Moon. That event reshaped our planet completely, melting the surface and changing the structure of the interior. Mars shows signs of something similar, but not exactly the same. The difference between the northern and southern hemispheres is one of the most unusual features on any planet in the solar system. The southern half is high, heavily cratered, and very old. The northern half is lower, smoother, and looks like it was resurfaced at some point. One explanation is that a giant impact early in Mars's history blasted away a huge part of the crust, leaving behind the basin that later became the northern plains. If that is true, the collision would have been one of the largest events in the solar system's history. An impact that big would not only change the surface, it could affect the core. It could change the thickness of the crust. It could alter the way heat moves through the planet. That might explain why Mars cooled differently from Earth, why its magnetic field disappeared earlier, and why its interior stayed active in some regions longer than expected. In other words, the planet we see today might not be the planet Mars was supposed to be. It might be the result of events that forced it onto a different path. There is another detail that makes this idea even more interesting. When scientists study meteorites that came from Mars, they find that the planet formed very quickly, within just a few million years after the solar system began. Earth, by comparison, took much longer to finish forming. That means Mars may be one of the oldest intact planets we can study. It formed early, it stopped growing early, and it kept the record of that early time. Because Earth continued to change, we lost most of the evidence from the first tens of millions of years. Mars did not. Its surface still carries marks from that chaotic period when planets were still being assembled. That is why the origin of Mars matters so much to scientists. It is not just about one planet. It is about understanding what the solar system looked like before it settled down, when there may have been more worlds than we see now, when orbits were shifting, when collisions were common, and when the difference between becoming a planet like Earth or a planet like Mars might have depended on only one or two events. And the more we learn, the more it feels like Mars was standing right on the edge between those possibilities, close enough to become a world with oceans, close enough to stay warm, close enough to keep an atmosphere, but not quite. In the next part, we're going to look even deeper into the strange differences between Earth and Mars, and why two planets that started so similarly ended up becoming completely different worlds. When scientists compare Earth and Mars, the similarities are impossible to ignore at first. Both are rocky planets. Both formed in the inner solar system. Both have volcanoes, mountains, valleys, and polar ice. Both show clear evidence that water once existed on their surfaces. If you look only at the early stages of their history, it almost seems like the two planets were following the same path. And yet, today, they could not feel more different. Earth is warm, covered in oceans, filled with air, and constantly changing. Mars is cold, dry, quiet, and almost frozen in time. Understanding how two planets that started so similarly ended up so far apart is one of the biggest clues to the origin of Mars, because the differences between them may not come from what happened at the end of their history, but from the very beginning. One of the most important differences is size. Earth is about twice the diameter of Mars and more than 6 times as massive. That difference may not sound huge at first, but in planetary terms, it changes everything. A larger planet has stronger gravity, which means it can hold onto its atmosphere more easily. It can trap heat longer. Its interior stays active for billions of years. Its core can keep moving, generating a magnetic field that protects the planet from the sun. Mars, being smaller, was always at a disadvantage. Its gravity was weaker, so gases could escape more easily. Its interior cooled faster, so its core stopped moving sooner. Its magnetic field faded earlier, leaving the atmosphere exposed. But the strange part is that Mars did not start out as a completely cold, dead world. The evidence shows that for a time, it had many of the same ingredients Earth had. There was water, there was volcanic activity, and there was an atmosphere thick enough to allow weather. So the question becomes, why did Earth keep those things while Mars lost them? One answer may lie in how quickly the planets formed. Studies of isotopes in Martian meteorites suggest that Mars formed very early, possibly within the first few million years after the Sun ignited. Earth, on the other hand, kept growing for tens of millions of years, collecting more material, absorbing more heat, and building a larger core. Because Mars formed fast, it may have locked in its structure before the solar system finished settling down. That means whatever conditions existed at that moment, the amount of heat, the materials available, the position of the giant planets, would have had a stronger effect on Mars than on Earth. In a way, Mars may be like a snapshot of an early version of the solar system, frozen before everything reached its final form. There is also the matter of where the planets formed. The inner solar system was not perfectly uniform. The farther you moved from the Sun, the cooler the material became, and the types of elements available changed slightly. Even a small difference in distance could affect how much metal, rock, or ice ended up inside a growing planet. Some scientists believe Mars may have formed slightly farther from the Sun than Earth did, or from material that came from a different region of the dust cloud. That would explain why its composition is not exactly the same, even though it is still similar enough to belong to the same group of rocky planets. If Mars started out with slightly different ingredients, that difference could have affected how its core formed, how its mantle cooled, and how long its magnetic field lasted. And when you combine that with its smaller size, the result is a planet that looked Earth-like for a while, but could not stay that way forever. There is another factor that makes the comparison even more interesting. Earth experienced a massive collision early in its history, when a Mars-sized body struck the young planet. That impact is believed to have created the Moon. It also melted much of Earth's surface and may have mixed the interior, helping the core stay hot and active for a longer time. Mars does not seem to have had an event exactly like that, at least not one that affected the entire planet the same way. It was hit many times, and one impact may have created the northern lowlands, but nothing appears to have remelted the whole world the way the moon-forming impact did for Earth. That difference may have been crucial. Earth was shaken, melted, and rebuilt. Mars was damaged, but never completely reset. Because of that, Earth may have stayed active longer, while Mars slowly cooled and settled into a quieter state. The core of Earth kept moving, the magnetic field stayed strong, and the atmosphere remained protected. Mars, without those advantages, began to lose its air, its water, and its warmth. But even that explanation may not tell the whole story. There are still details about Mars that do not fit perfectly into any single model. The thickness of its crust, the size of its core, the strange difference between its hemispheres, and the evidence of long-lasting volcanic activity all suggest that the planet's history was more complicated than just small planet, cooled fast. Some researchers think the early solar system may have gone through several periods of instability, when the orbits of the giant planets shifted and the inner worlds were affected in ways we are only beginning to understand. During those times, the material that formed Mars could have been scattered, mixed, or partially removed. That could mean Mars never had the chance to become as large as Earth, not because it could not, but because the conditions changed before it finished forming. It is like a building that stopped halfway through construction. The foundation is there, some of the structure is there, but the rest was never completed. And because it stopped early, it preserved details that the finished building would never show. That may be why Mars is so valuable to scientists. It is not just another planet to explore, it is a record of a time when the solar system was still uncertain. Every valley, every crater, every ancient rock on Mars tells part of the story of how the planets formed, how they changed, and how close some of them came to becoming something very different. And the closer we look, the more it feels like Mars was always right on the edge between two possibilities. One path could have made it another Earth. The other turned it into the quiet red world we see today. In the next part, we're going to explore some of the strangest clues scientists have found on Mars. Clues that suggest the planet's past may have been even more active and even more mysterious than we once believed. As missions to Mars became more advanced, the questions about its origin only grew more complicated. Every new orbiter, every rover, every lander sent back information that made the red planet feel less like a simple frozen world and more like a place with a long, complicated history that we are still trying to understand. At first, scientists expected Mars to be geologically quiet, a small planet, cooled long ago, with nothing happening except dust storms and the slow fall of meteorites. But the closer we looked, the more we found signs that Mars stayed active much longer than anyone predicted. Some of the most surprising clues came from the surface itself. There are regions on Mars where the ground looks cracked and folded, as if the planet's crust shifted after it had already cooled. There are lava flows that appear younger than the surrounding terrain, suggesting that volcanic activity continued long after the early era when Mars was supposed to have lost most of its heat. There are even slopes where dark streaks appear and disappear over time, leading scientists to wonder if something beneath the surface might still be moving today. None of these signs mean that Mars is alive in the way Earth is, but they do suggest that the planet did not become completely inactive as early as we once thought, and that makes its origin even more interesting. Because if Mars stayed warm longer than expected, then something inside the planet must have kept heat trapped for a very long time. One of the biggest clues comes from the thickness of the Martian crust. Measurements from orbit and from seismic data show that the crust of Mars is much thicker than Earth's, and in some places, it may be thicker than scientists thought possible for a planet of its size. A thick crust can act like insulation. Instead of letting heat escape quickly, it can trap warmth inside the planet, slowing the cooling of the interior. That could explain why volcanoes stayed active longer, why some regions look younger, and why the core may still contain molten metal even today. But a crust that thick raises another question. Why did Mars develop such a heavy outer layer in the first place? If it formed exactly the same way as Earth, the crust should have been thinner, more like the crust of our own planet. The fact that it isn't suggests that something about the early history of Mars was different. Maybe it formed from material that cooled faster. Maybe it experienced impacts that changed the way its interior settled. Maybe the early solar system was more uneven than we imagine. There is also the strange difference between the two halves of Mars, the northern lowlands and the southern highlands. This contrast is one of the most dramatic features on any planet in the solar system. The southern hemisphere is covered in ancient craters, showing that it has not changed much for billions of years. The northern hemisphere is smoother, lower, and looks like it was reshaped long after the planet first formed. One explanation is the giant impact theory. According to this idea, early in Mars history, a huge object struck the planet with enough force to melt part of the crust and create the enormous basin that covers much of the northern half. The collision would have been powerful enough to change the structure of the entire planet, possibly affecting the core, the mantle, and even the magnetic field. If that impact happened while Mars still had a thick atmosphere, it could also have blown a large part of it into space. That would mean the loss of the atmosphere was not just a slow process caused by the solar wind, but also the result of one or more violent events that stripped the planet of its protection. Some researchers think this may have been the moment when Mars passed the point where it could no longer stay warm. Before the impact, the planet might have had a stronger magnetic field, more volcanic activity, and a thicker atmosphere. After the impact, the balance may have been broken. The core cooled faster, the magnetic field faded, the atmosphere began to escape, water froze or vanished. From that point on, Mars may have been slowly moving toward the cold state we see today. But even with that explanation, there are still things about Mars that do not fully make sense. For example, some regions show signs of sudden floods that seem to have happened long after the atmosphere should have been too thin for liquid water to exist. These floods carved enormous channels in a short time, leaving behind features that look as if huge amounts of water burst out from underground. That suggests that water may have been trapped beneath the surface, frozen under layers of rock and ice, and then released when pressure built up or heat melted the ground. If that is true, Mars may have held onto more water than we thought, hidden below the surface long after the climate became cold. There are also hints that some volcanic activity may have continued much later than expected. Certain lava flows look younger than the surrounding terrain, and some areas appear to have been reshaped in ways that suggest heat was still present deep underground. None of this means Mars is active now in the way Earth is, but it does mean the planet's history was not as simple as once believed. Instead of cooling steadily from hot to cold, Mars may have gone through several stages. A warm beginning, a period of change and instability, a slow loss of atmosphere, bursts of activity even after it seemed too late, and finally, the quiet world we see now. When you look at that timeline, the origin of Mars starts to feel less like a straight line and more like a path full of turns. Small differences in the beginning could have led to huge changes later. A slightly smaller size, a slightly different orbit, one extra collision, one missing event. Any of these could have pushed the planet toward a completely different future. And that is why scientists keep studying Mars so carefully, because it shows how close a world can come to being like Earth, and how easily that chance can be lost. In the next part, we're going to explore one of the most fascinating ideas about the origin of Mars, the possibility that the early solar system once contained more worlds than we see today, and that Mars may be one of the few survivors of that forgotten time. When scientists look back to the earliest days of the solar system, they no longer imagine a calm place where planets slowly formed in neat, predictable paths. The more we study how planetary systems develop, the more it becomes clear that the beginning was crowded, unstable, and full of worlds that no longer exist. Mars may be one of the last remaining clues from that forgotten time. In the standard picture, the inner solar system eventually settled into 4 rocky planets: Mercury, Venus, Earth, and Mars. but computer simulations that try to recreate the formation of those planets often produce very different results. Instead of 4 worlds, the models frequently create many more, sometimes 10, sometimes 20, all forming at the same time, all competing for the same material. These early worlds, sometimes called planetary embryos, were not small. Many of them would have been as large as the Moon, and some could have been nearly the size of Mars or Earth. They moved through the young solar system in unstable orbits, pulled by gravity, colliding with each other, merging, breaking apart, or being thrown outward into space. In that environment, nothing was guaranteed. A planet that looks permanent today may only be here because it survived when others did not. This idea becomes especially important when we look at the region where Mars formed. Between Earth and Jupiter, there should have been enough material to create another large planet. Instead, we see a small Mars and the asteroid belt, a scattered collection of fragments that never became a world. That gap has puzzled scientists for a long time. Why is Mars so small compared to Earth? Why didn't another planet form in the asteroid belt? Why does the inner solar system look incomplete? One possible answer is that the solar system once had more planets, but they did not all survive. Some models suggest that during the first 100 million years, the orbits of the giant planets, Jupiter, Saturn, Uranus, and Neptune, were not the same as they are now. As these massive worlds moved, their gravity could have disturbed the inner solar system, scattering material, changing orbits, and even ejecting entire planets into deep space. This idea is part of what scientists call the Nice model, named after the city in France where the theory was first developed. According to this model, the giant planets may have shifted positions long after they formed, causing a chain reaction of gravitational disturbances that affected everything around them. If that happened, the inner planets may have been reshaped by those changes. Some worlds could have been pushed into the sun. Some could have collided with each other. Some could have been thrown completely out of the solar system. Mars may have survived that period, but not without being changed by it. In fact, its small size may be the result of that chaos. If Jupiter moved inward and then back outward, as some versions of the Grand Tack theory suggest, it could have cleared out much of the material that would have helped Mars grow. Instead of becoming a planet as large as Earth, Mars may have been left with only a small amount of the original building material. It formed early, it stopped growing early, and it stayed small. At the same time, the asteroid belt may be what remains of the material that never got the chance to form a planet at all. Some of it may even be pieces of worlds that were destroyed before they could fully develop. There is another idea that makes the origin of Mars even more mysterious. Some researchers have suggested that there may once have been an additional rocky planet in the inner solar system, a world that no longer exists today. In certain simulations, the system becomes more stable if there was originally one extra planet that was later lost. This missing world might have been about the size of Mars, or slightly larger. During the early period of instability, it could have collided with another planet, been thrown out of the solar system, or been pulled into the sun. If something like that happened, the effects would still be visible today. The orbits of the remaining planets would be slightly different. The distribution of asteroids would not be uniform. Some planets would be smaller than expected. Mars could be one of the planets whose history was shaped by that missing world. Perhaps it lost material during a collision. Perhaps its orbit was changed. Perhaps the disturbance prevented it from growing larger. We may never know exactly what happened, because most of the evidence from that time has been erased. Earth's surface has been recycled again and again. Venus may have been completely reshaped by volcanic activity. Mercury has been heavily altered by impacts. Mars, however, kept much of its ancient surface. Because it cooled early and never developed strong plate tectonics, the oldest rocks are still there, carrying marks from a time when the solar system was still settling into its final form. That makes Mars one of the best records we have of that early chaos. And when scientists study those ancient regions, they sometimes find signs that the planet's history was more violent than we once imagined. Huge impact basins, deep fractures, and strange differences in the crust all suggest that Mars did not simply form and stay the same. It was shaped by events that we are only beginning to understand. There is also the possibility that Mars itself played a role in shaping other worlds. If the early solar system had more planetary embryos than it does now, some of them may have collided with Earth or Venus. The object that struck Earth and created the Moon was about the size of Mars. It is possible that more than one Mars-sized world existed at that time, and only one of them survived in its original form. That would mean the planet we see today is not just another neighbor. It is a survivor from an era when the solar system had more worlds than it does now, when the final arrangement of planets was not yet decided, when the difference between becoming Earth, Mars, or nothing at all could depend on a single collision. When you think about Mars that way, its origin feels less like a simple story and more like the result of countless chances, accidents, and changes that happened billions of years ago. A slightly different orbit, a slightly different collision, a slightly different amount of material, and Mars might not exist at all, or it might have become something completely different. In the next part, we're going to look at one of the most intriguing questions about the red planet: why Mars kept so many signs of its ancient past, while Earth lost most of its own, and how that makes Mars one of the most important worlds for understanding the hidden history of the solar system. One of the reasons Mars has become so important to scientists is not just because of what it is, but because of what it still remembers. When we try to study the earliest history of Earth, we quickly run into a problem. Our planet has changed too much. The surface is constantly being recycled. Oceans move, continents shift, volcanoes erupt, and over millions of years, the oldest evidence disappears. Mars did not go through that same kind of constant renewal. Because it is smaller, its interior cooled faster. Because it cooled faster, its crust became thick and stable early in its history. And because the crust stayed mostly in place, the surface kept the marks of events that happened more than 4 billion years ago. In a way, Mars became a time capsule, preserving details from the earliest days of the solar system that Earth can no longer show us. When scientists study the oldest regions of Mars, especially the southern highlands, they are looking at terrain that formed when the planets themselves were still new. These areas are covered in craters, each one a reminder of how violent the early solar system was. Back then, impacts were not rare accidents. They were part of everyday life for a young planet. Asteroids, comets, and leftover fragments from planet formation were constantly crossing paths. Some were small, some were large, and some were big enough to change the entire structure of a world. Mars was struck many times, and those impacts left scars that never fully disappeared. Because those scars are still visible, Mars gives us a clearer picture of what the inner solar system looked like before everything settled down. It shows us that the early period was not smooth or orderly. It was chaotic, full of collisions, shifts in orbit, and changes that could completely alter the future of a planet. This is one of the reasons the origin of Mars is so closely connected to the origin of the entire solar system. When we understand why Mars formed the way it did, we learn something about why Earth formed the way it did too. The two planets are like different outcomes from the same beginning. One grew large, stayed warm, and kept its atmosphere. The other stopped early, cooled faster, and slowly lost what it had. And the difference between those outcomes may have been surprisingly small. One of the most interesting clues comes from the ages of Martian rocks. Measurements from meteorites and surface analysis suggest that Mars finished forming very quickly, possibly within the first 10 million years after the solar system began. Earth took much longer to reach its final size, growing through a series of collisions over tens of millions of years. That means Mars locked in its structure early, before the solar system had completely stabilized. Whatever conditions existed at that moment became part of the planet permanently. If the giant planets moved later, Mars could not grow larger to adapt. If material was scattered away, Mars could not replace it. If an impact changed its interior, the planet did not have enough heat left to fully recover. In a sense, Mars may be the most ancient planet we can study without digging into Earth's deepest layers. And that ancient nature shows up in its chemistry as well. When scientists examine Martian meteorites, they find small differences in the ratios of certain elements compared to Earth. These differences suggest that the material that formed Mars may not have come from exactly the same part of the original dust cloud as the material that formed our planet. It is still part of the inner solar system, but not perfectly identical. That raises the possibility that the region where Mars formed was influenced by events that did not affect Earth as strongly. Perhaps Jupiter's gravity disturbed the dust in that area. Perhaps material from farther out was mixed in. Perhaps collisions moved pieces of growing planets into new positions. Each of these possibilities makes the origin of Mars feel less predictable. Instead of a clean, simple formation, the planet may have been shaped by a series of changes that happened at just the right time to keep it small, to alter its structure, and to set it on a different path from Earth. There is also the question of why Mars kept its ancient surface, while Earth did not. On Earth, the movement of tectonic plates constantly reshapes the crust. Old rock sinks back into the mantle, new rock rises, and over long periods, the oldest evidence disappears. This process helps keep Earth active, but it also erases the past. Mars never developed strong plate tectonics. Its crust became thick and rigid early on, and once that happened, the surface stopped moving very much. Volcanoes continued in some regions, and impacts still occurred, but the planet did not recycle its crust the way Earth does. Because of that, the oldest layers remained on top. That makes Mars one of the best places to study the early solar system, because it still shows what the surfaces of young planets looked like before billions of years of change erased the details. And those details tell us something important. They tell us that the difference between becoming Earth or becoming Mars may not have been a huge difference at all. It may have been the result of timing, size, and a few critical events that happened in the first 100 million years. If Mars had been slightly larger, it might have held onto its heat longer. If its magnetic field had lasted longer, it might have kept its atmosphere. If one impact had happened differently, the planet might have stayed warm. That idea makes the red planet feel less like a failed world, and more like a world that almost became something else. And that is why scientists keep returning to the question of its origin. Because Mars may not only tell us how planets form, it may tell us how close a planet can come to being like Earth, and how easily that chance can disappear. In the next part, we're going to move even deeper into the strange possibilities surrounding Mars's past, including the idea that the planet may have gone through changes we still don't fully understand, and why some scientists think the early solar system may have been far more unstable than we ever imagined. The deeper scientists look into the early history of Mars, the more they realize that the solar system may have been far less stable than it appears today. We tend to think of the planets as permanent, fixed in their places, following the same paths around the sun forever. But in the beginning, nothing was that certain. The first few 100 million years were a time when orbits shifted, worlds collided, and entire regions of space were rearranged. Mars seems to carry the marks of that unstable era more clearly than almost any other planet. One reason for that is its size. Because Mars never grew as large as Earth or Venus, it never developed the same long-lasting internal activity that would have erased its past. Its surface became quiet early, and once it did, the the planet stopped rewriting its own history. The valleys, the craters, the ancient volcanic plains, all of them remained almost exactly as they were when the solar system was still young. When scientists study those ancient regions, they sometimes see patterns that suggest the early solar system went through several periods of disruption, not just one. Instead of forming once and then settling down, the planets may have been reshaped again and again before reaching their final arrangement. One of the strongest pieces of evidence for this comes from the orbits of the giant planets. Jupiter, Saturn, Uranus, and Neptune are so massive that even small changes in their positions can affect the entire solar system. Modern models suggest that these planets may not have formed exactly where they are today. After they formed, they may have moved, slowly at first, and then more suddenly as their gravity pulled on each other. If that happened, the effects would not have been limited to the outer solar system. The inner planets could have been affected as well. When a giant planet shifts its orbit, it changes the gravitational balance everywhere. Regions that once had enough material to form large planets might suddenly lose that material. Objects that were moving in stable paths could be thrown into new ones. Growing worlds could collide or break apart before they had time to finish forming. Mars sits right in the region where those changes could have had the biggest impact. Between Earth and Jupiter, the balance of gravity is delicate. A small disturbance from a giant planet could scatter dust and rock away from the area, leaving less material for a planet to grow from. If that happened early enough, Mars might have formed quickly from what was available, but then stopped growing when the rest of the material was pulled away. That would explain why the planet looks like it began forming normally, and then suddenly slowed down. There is also evidence that the asteroid belt may be part of the same story. Instead of being leftover material that never formed a planet, the belt may be what remains after the early solar system was disturbed. Pieces of rock from different regions were mixed together, some pushed inward, some pushed outward, until the area between Mars and Jupiter became a place where no large planet could survive. In that case, Mars might be the last planet that managed to form in that region before the chaos cleared everything else away. Some scientists have gone even further, suggesting that the early solar system may have once contained an extra planet that no longer exists. In certain simulations, the system becomes more stable if there was originally one more rocky world that later disappeared. This missing planet could have been about the size of Mars, or even larger. If such a planet existed, its loss would have changed everything. A collision between two early planets could scatter debris across the inner solar system. A world thrown out by Jupiter's gravity could leave the remaining planets in new orbits. Even a close encounter between growing planets could strip material away and prevent one of them from reaching its full size. Mars could be the result of one of those events. Not destroyed, not completely changed, but altered enough that it never became what it might have been. Its small size, its thick crust, its early cooling, and its unusual surface could all be the result of conditions that no longer exist anywhere else. There is another detail that makes Mars feel like a survivor from a different time. When we look at Earth, most of the oldest rocks are gone. Plate tectonics has recycled the crust again and again, melting, reshaping, and replacing the surface over billions of years. On Mars, that never happened. The crust stayed in place, and the ancient layers remained exposed. That means the southern highlands of Mars may be one of the oldest intact surfaces in the entire solar system. When scientists date those rocks, they find ages going back more than 4 billion years, to a time when the planets were still forming and the sun itself was young. Those regions show us what the inner solar system looked like before the final arrangement of planets was finished. And what they show is not calm. They show a world that was hit again and again, shaken by impacts, covered in volcanic flows, and carved by water that flowed when the atmosphere was thicker. They show a planet that formed quickly, changed suddenly, and then slowly went quiet, while everything else kept evolving. That is why Mars feels different from the other planets. Mercury is too close to the Sun to hold many clues about its early past. Venus has been reshaped so much that its oldest history is hidden. Earth has erased most of its beginnings through constant change. Mars is the one place where the past is still visible. And because of that, it keeps reminding us that the solar system we see today may not be the only one that ever existed. The early system may have had more planets, different orbits, and events so violent that entire worlds disappeared. Mars may be what remains after all of that settled down. A planet that formed early, survived the chaos, and then slowly lost the conditions that might have made it more like Earth. In the next part, we're going to explore one of the most haunting ideas about the origin of Mars. The possibility that the planet once had everything it needed to stay warm and alive, and that only a few small changes in the early solar system may have decided its fate. When scientists try to imagine what Mars looked like in its earliest days, the picture can feel surprisingly familiar. Instead of the cold red desert we know now, the planet may once have had clouds moving across the sky, rivers cutting through valleys, and lakes resting in wide basins. The surface would not have looked exactly like Earth, but it may have been close enough that, from a distance, the two planets could have seemed like part of the same story. That idea is one of the most haunting parts of studying Mars, because when we follow the evidence back far enough, it begins to look as if the red planet once had everything it needed to stay warm. It had volcanic activity releasing gases into the atmosphere. It had enough gravity to hold that atmosphere, at least for a time. It had water, not just frozen underground, but flowing across the surface. And it had heat inside, enough to keep the planet active long after it formed. If those conditions had lasted, Mars might have remained a world much more like Earth. But something changed. One of the key differences between the two planets may have been the strength of their magnetic fields. Earth's magnetic field is still strong today, created by the motion of liquid metal in its core. That field protects the atmosphere from being stripped away by the solar wind. Without it, our planet would slowly lose air the same way Mars did. Mars had a magnetic field once, but it did not last. When the core of Mars cooled, the movement of molten metal slowed, and the magnetic field weakened until it disappeared completely. Without that invisible shield, the solar wind began to erode the atmosphere. It did not happen all at once. It happened slowly, over millions of years, but the result was the same. The air became thinner. The pressure dropped. The planet grew colder. Once the atmosphere reached a certain point, liquid water could no longer stay on the surface. Even if ice melted, it would either freeze again or turn directly into vapor and escape into space. The rivers that once carved valleys stopped flowing, and the lakes that once filled craters slowly vanished. But the strange part is that this change may not have been inevitable. Some models suggest that if Mars had been just a little larger, its core might have stayed hot longer. If the magnetic field had lasted a few 100 million years more, the atmosphere might have remained thick enough to keep water on the surface. If one or two early impacts had happened differently, the planet might have kept the heat it needed to stay active. In other words, Mars may not have been doomed from the beginning. It may have been very close to becoming another Earth. That idea becomes even more interesting when we look at the timing of the changes. Evidence suggests that Mars lost its magnetic field very early, possibly while the planet still had rivers and lakes. That means there may have been a long period when Mars was slowly losing its atmosphere, but had not lost it yet. During that time, the planet could have been in a fragile balance, warm enough for water, thick enough air for weather, active enough to keep the surface changing. A balance like that does not need a huge event to break. A single large impact, a shift in volcanic activity, or a change in the sun's behavior could push the planet past the point where it could no longer recover. Some scientists think that may be exactly what happened. There is evidence that Mars experienced at least one enormous collision early in its history, possibly the impact that created the northern lowlands. If that event happened while the planet still had a thick atmosphere, it could have thrown huge amounts of gas into space. It could also have disturbed the core, changing the way heat flowed inside the planet. After that, the magnetic field might have faded faster. The atmosphere might have escaped more quickly. The climate might have cooled beyond the point where water could stay liquid. From that moment on, Mars may have been moving toward the cold world we see now, even if it took millions of years to get there. There is another possibility that makes the origin of Mars feel even more uncertain. Some researchers believe the early solar system may have gone through several periods of instability when the orbits of the giant planets shifted and the inner worlds were affected in ways we still do not fully understand. During those times, Mars could have been pushed into a slightly different orbit, changing the amount of sunlight it received. Even a small change in distance from the Sun can affect a planet's climate over long periods. If Mars moved only a little farther away, it might have become colder sooner. If it moved slightly inward before settling into its current orbit, it might have stayed warmer for longer than we expect. These changes are difficult to prove, but the models show that the early solar system was flexible enough for them to happen. That means the fate of Mars may have depended on events that lasted only a short time compared to the age of the solar system. A shift that happened millions of years after the planets formed could still decide what Mars would become billions of years later. When you think about it that way, the red planet feels less like a failure and more like a near miss. It had the right ingredients. It had the right conditions for a while. It had a chance to become something very different. But the balance did not hold. And because it did not hold, Mars became something unique. A planet that shows us what the early solar system looked like and what can happen when a world loses just enough heat, just enough air, or just enough time. In the next part, we're going to begin moving toward the end of the story, looking at why Mars remained frozen in this state for billions of years, and why it still keeps secrets that scientists are only starting to understand. After Mars lost the conditions that once made it warm and active, the planet entered the longest chapter of its history. For billions of years, very little changed compared to the violent and unpredictable beginning. The rivers stopped flowing, the atmosphere thinned to almost nothing, and the surface settled into the quiet state we see today. But even in that silence, Mars kept the record of everything that happened before. That is one of the reasons the planet feels so mysterious. On Earth, the past is constantly being erased. The surface moves, oceans shift, continents break apart and come back together. Even the oldest mountains are young compared to the age of the planet itself. Mars is different. Once it cooled and became stable, the surface stayed mostly the same. Craters remained where they formed. Valleys stayed where water carved them. Volcanic plains hardened and never moved again. Because of that, Mars became a kind of archive. Every layer of rock, every fracture in the crust, every ancient basin tells part of the story of how the planet formed and how it changed. When scientists send orbiters and rovers to Mars, they are not just exploring another world. They are reading a record written billions of years ago, a record that Earth can no longer show. One of the most important things that record reveals is how close Mars came to following the same path as our planet. In its earliest era, Mars had heat inside, water on the surface, and an atmosphere thick enough to support weather. Volcanoes were active, releasing gases that built the air. The magnetic field protected that air from the sun. For a time, the planet had everything it needed to stay warm. But because Mars was smaller, it could not hold those conditions forever. The core cooled faster, and once it cooled, the magnetic field weakened. Without the magnetic field, the atmosphere slowly escaped. Without the atmosphere, the temperature dropped. Without warmth, water could no longer stay liquid. Each step led to the next, until the planet reached a point where it could not go back. What makes this story so striking is how small the differences may have been. If Mars had been only a little larger, its core might have stayed hot longer. If its magnetic field had lasted longer, the atmosphere might have survived. If one early impact had happened differently, the balance might not have been broken. Those small differences could have changed everything. Instead of a frozen desert, Mars might have remained a world with oceans. Instead of a thin sky filled with dust, it might have had clouds and rain. Instead of being silent for billions of years, it might have continued to change the way Earth does. But the solar system does not guarantee outcomes. The early years were full of chance, full of collisions, full of shifting orbits and unstable paths. Some planets grew large enough to stay active. Others stopped too soon. Mars seems to have been right on the edge between those two possibilities. It formed quickly, but not large enough. It stayed warm for a while, but not long enough. It held an atmosphere, but not strong enough to keep it forever. Because of that, Mars became something unique. A world that shows us what happens when a planet almost becomes like Earth, but not quite. Even now, billions of years later, the planet still holds hints that its story is not completely finished. Beneath the surface, there is still ice and possibly liquid water trapped deep underground. The core may still contain molten metal. Some regions show signs of activity that happened far later than scientists once believed possible. Nothing on Mars changes quickly anymore, but that does not mean nothing changes at all. The dust still moves in great storms that can cover the entire planet. The polar ice grows and shrinks with the seasons. Small landslides appear on slopes where the ground shifts. Deep underground, there may still be warmth left from the time when the planet was young. All of these things remind us that Mars is not just a dead world. It is a world that lost its chance to stay alive. And that makes its origin one of the most important stories in the solar system. Because by understanding why Mars became what it is, we learn something about how planets form, how they survive, and how easily their future can change. When scientists study Mars, they are not only trying to understand the red planet, they are trying to understand why Earth did not end up the same way, why one world kept its oceans while the other lost them, why one world stayed warm while the other froze, why one world became the place where we live, and the other became a quiet reminder of how different things could have been. In the next part, we will finish this journey, looking at what Mars still teaches us today, and why the story of its origin continues to shape the way we think about planets, life, and the hidden history of the solar system. When we reach the end of the story of Mars, it does not feel like the end of a mystery. It feels more like the moment when we realize how much of the mystery is still there. The red planet sits where it always has, moving slowly around the sun, silent, cold, and unchanged to the eye. But every time we look closer, every time we send another spacecraft, every time we study another piece of rock that once came from its surface, the past of Mars becomes a little clearer and a little stranger. What makes Mars so fascinating is not just that it is different from Earth, but that it almost wasn't. In the earliest days of the solar system, the inner planets began with the same basic ingredients: dust, rock, metal, heat, and time. Gravity pulled those ingredients together, collisions shaped them, and the young sun lit them from the center of the growing system. For a while, Mars followed the same path as Earth and Venus. It formed quickly, gathered enough material to become a real planet, and held onto the heat left over from its creation. For a time, that was enough. Volcanoes released gases that built an atmosphere. The core moved, creating a magnetic field. Water collected on the surface. The planet changed, just as Earth was changing. If you could have seen Mars during that era, it might not have looked like the world we imagine now. The sky may have been thicker, the ground darker, the air filled with clouds and storms instead of dust. Rivers may have cut through the land, and lakes may have filled the low places where today there is only dry rock. It was not Earth, but it was not the frozen desert we know either. Then, slowly, the balance began to shift. Because Mars was smaller, it could not keep its heat as long. The core cooled faster. The magnetic field weakened. Without that invisible shield, the solar wind began to pull the atmosphere away. Not in a single moment, not in one disaster, but in a slow, steady loss that took millions of years. At the same time, the early solar system was still changing. The giant planets moved, disturbing the paths of smaller worlds. Impacts reshaped the surfaces of the inner planets. Material that once could have formed new worlds was scattered or lost. Somewhere in that unstable time, Mars stopped growing. It kept what it had, but it never became larger, never gained enough mass to hold onto its warmth forever. One by one, the things that made the planet active began to fade. The volcanoes slowed, the air grew thin, the water froze or escaped, the surface grew quiet. By the time the solar system settled into the stable pattern we see today, Mars had already become something different from the world it once might have been. It was no longer on the path toward becoming another Earth. It had crossed the point where it could not go back. And yet, that is exactly why it is so important. Because Mars did not change the way Earth did, it kept the record of those early times. Its surface still shows the scars from the era when planets were still forming. Its rocks still carry the signs of ancient water. Its crust still holds the magnetism from a field that vanished billions of years ago. When we look at Mars, we are looking at a memory of the solar system before it became calm. We are seeing what the inner planets looked like when their future was not decided yet. A time when there may have been more worlds than we see now. A time when orbits shifted, when collisions were common, and when the difference between becoming a living world or a silent one depended on only a few small changes. That is why the origin of Mars feels so different from the origin of the other planets. It is not just the story of how a world formed. It is the story of how close a world came to becoming something else. And even now, Mars still keeps secrets. Beneath the surface, there may still be water frozen in the ground. Deep underground, there may still be warmth left from the time when the planet was young. In the rocks, there may still be chemical traces from an atmosphere that no longer exists. Every mission we send finds something new, something that makes the story a little more complicated. Not because the planet is hiding anything, but because the past is never as simple as we first imagine. Maybe Mars was always meant to end this way. Maybe it never had the mass to stay warm forever. Maybe every small world eventually cools and grows silent. Or maybe the early solar system could have turned out differently. Maybe if one orbit had shifted another way, if one collision had happened sooner, if one planet had grown just a little larger, Mars might not be the red desert we see tonight in the sky. It might have been a world with oceans, a world with clouds, a world that kept its atmosphere and never lost its chance to stay alive. And when you look up at that small red light drifting slowly across the darkness, it is hard not to feel that strange sense of what could have been. A planet that almost followed the same path as Earth, and then quietly went another way. So tonight, as you let your mind drift and your thoughts slow down, imagine the solar system as it once was. Not the calm, ordered place we know now, but a younger sky filled with dust, fire, and growing worlds. Imagine Mars in that distant time, warm beneath a thicker sky, its surface changing, its future not yet decided. Somewhere in that ancient moment, the path of the planet turned. And billions of years later, the red world still carries the memory of that turn, moving silently through space, holding the secrets of its origin, waiting for us to keep asking questions. If you enjoyed drifting through this story with me tonight, don't forget to subscribe to Sleepy Tin Foil Hat and leave a comment telling me where you're listening from. I always like seeing how far these late-night journeys travel across the world. For now, there's nothing else you need to think about. Let the questions fade. Let the images drift away. Let your breathing slow and your mind grow quiet. The planets will keep moving. Mars will keep circling the sun, and the story of its origin will still be there, waiting for another night. Sleep well.